So welcome to today's lecture in the course Remote Sensing Image Analysis and Interpretation. And today we will talk about classification with Bayes' theorem and also how you can evaluate a classifier. And I want to start with classification with Bayes' theorem. So far we were talking about two different classifiers. One was decision tree and the other one was k-nearest neighbor. And decision tree is nothing else than a hierarchy of decision rules, and it's a discriminative classifier because the overall goal is to discriminate between different classes. K-nearest neighbor is a generative classifier, and here it is assumed that the given training data reflects the distribution of all the classes. And depending on the frequency of a class in the neighborhood of a test sample, you can derive the probability of the class membership of this test sample. So if you have 5 samples, training samples around the given test sample, and 3 of them belong to class 1 and the other 2 belong to class 2, you have a higher percentage that the test sample belongs to the class 1 than to class 2. And so far we were not talking about probabilities, but actually this is can be quite helpful, especially if you want to make decisions under uncertainty. And when we want to talk about decisions and probability, we first need to think about decision theory, because classification is based on decision theory. And decision theory is, there are two core steps. One is inference and the other one is decision making. So inference is making conclusion based on evidence and reasoning. So given evidences and knowledge you have, you make an educated guess and come to a conclusion. And in the decision making step, the actual decision is made. And so this is the actual act of choosing between different courses of action. So the actual decision-making process is based on the inference and external factors independent of the data. Because sometimes you want to prefer one decision over another because one decision might be more useful or less risky. And as I said, so far no probabilities were involved in the inference process, and today we will deal with inference in the style of Bayes, and so we will introduce probabilities. And this will lead us to Gaussian maximum a posteriori estimator and Gaussian maximum likelihood classification. So let's start with the Bayes theorem. So the Bayes theorem is illustrated here. Let's go first through the notation. So phi is the feature, and this can be a vector, for example, red, green, and blue, or near infrared, or whatever features you want to have. Last lecture we were talking about feature extraction, so this is actually where you need it. So CK are the classes, and K is the index for the class. The capital P is a probability. Probabilities are discrete values, and for each class the values are between 0 and 1, and also for all classes they sum to 1. And there's also a small p in this equation, and this is a function value. It can be seen a little bit similar to probability, but it's actually not a probability because it does not have all these characteristics I mentioned before. And the question is now, what is the probability of a class given the feature? And so let's now go through the single components after we introduced what we actually are aiming for and the notation. Let's have a look at the single terms in the Bayes theorem. So first of all, there is the likelihood function for a class K. So this likelihood function is given or you need to determine for each class K, and it's a value that indicates how likely it is that a specific feature occurs given a class K. Then you have an a priori probability, and this is the probability for the occurrence of a specific class. And as the name says, it's a prior value, and this is something what you know beforehand. And this term is also independent of the data. And then there is the a posteriori probability. So actually there are a few ones. For each class you have a posterior probability. And this is the probability that a specific class occurs given a feature. And this is what you want to determine. So on the left side, this is what you want. On the right side, this is what you need to compute. And there's one term left, which is the evidence. And the evidence is the occurrence of a specific feature. And this might be hard to grasp. And that's why let's have a closer look in how it is actually computed, because then it's easier to understand. The evidence serves as a normalization so that the posterior probability is actually a probability. And as I said, and also as I will show you on the slide here, for the left side you want to have a probability. And when you have a look how the evidence is computed, you will see that it is computed as the sum of the likelihood times the prior and summed over all classes. And what happens when you sum over all classes is that the term gets independent of the class. So this is this whole thing is called marginalization. So you're summing out the classes. And so in the end, you can think of this term as a normalization with the goal that your posterior probabilities are actually probabilities. And here's one example showing you how such a posterior probability vector can look like. So you have given here 3 classes, and you see they are all larger than 0. They are all between 0 and 1. And they sum to 1. And these are actually characteristics. And if some of the characteristics is missing, it's not, you cannot call it probability. And here you can see the Bayes theorem in short. So the Bayes theorem says nothing else than the posterior is likelihood times prior divided by the evidence. And on the left side, the posterior, this is what you want. And on the right side, this is what you need to compute to get the posterior. And so let's first have a look at the likelihood. And this is something what you can estimate from your training data. So now we actually start to think about classification and how we can use the Bayes theorem for classification. And as in all the previous lectures, I want to focus again on this example where you can see the arable lands, the agriculture area in the desert. And let's pick a small part of the image and let's focus on this for now. So let's assume for now we are focusing on the features, and as features we take red, green and blue as illustrated here, and we need training data. And here we, for simplicity, we collect training data by photo interpretation. That means we have a look at the image and we just make some scribbles. So we mark some areas which are arable land and which are desert. So this looks can look like this here. In the end, what an annotation is in detail is that you have some coordinates with labels, and you know exactly that a specific feature with a coordinate has a specific label. So because in the end you need this input-output pairs, and you need you need to assign them to each other. And so this is the annotation you need for training. So first of all, let's talk a little bit more about the annotation. It means the labeled data. In the end, it's your choice how you annotate the data and how you store it and represent it. But there's some simple rules you need to follow. So first of all, you take the annotation, that means the labeled data, and you divide it into training and testing set. As I said before, the training data is used to learn the model and the testing data is used to evaluate the model. The way you split the training and the test data is crucial, first of all, for the classification success, but also how the evaluation reflects actually how good your model is. Because if you have a wrong splitting, it might happen that your evaluation result is too positive and your model actually does not generalize well to unseen data. So be careful with the splitting. And also a rule is that never learn on the testing data. So once you have split it, training and testing data, just take the testing data and put it away. And just pretend it's not there. And everything what you do for learning the model is done with the training data. And one thing, there are so-called benchmarks out there. Benchmarks are data sets where you have a predefined splitting. And this makes easy for comparison, because when you can download data or when you just use any kind of data and you know, and everybody uses the same splitting, it's much more easier to compare between all the different methods which were applied to this benchmark data set. And in remote sensing, it's common to separate the data spatially. So this is what I mean when I talk about you need a proper splitting of the training and testing set, that in the end your evaluation actually reflects how good your model is. And I want to name two options. There are of course more, but two options that you can see how you can actually split the data, that you have a spatially disjoint training and testing set. The option one is that you split your data into polygons, and one set of polygons for training is used for training and the other one for testing. So when you see in this image, you have these red strokes for one class and the blue for other classes. All these different areas are spatially disjoint, and also, they are separated spatially. So you can take one part randomly, for example, use it for training and the other one for testing. What you should not do is that you randomly sample over all labeled data, because then you have neighboring, it can happen that you have neighboring testing and training samples, and because in remote sensing images you have a high spatial correlation of pixels, you will end up most likely with a result which is too positive. The second option is, it's quite similar, but can be in some cases much easier. You just take the annotated data in one half of the image for testing and in the other part for training. And this can look like this. So here the other upper half in the image is chosen to be the training data, and in the lower part is chosen for testing data. This is not always possible, because you need to be careful that all the classes are actually in these areas. So you should not have a training data set where a class is missing, and also try to get a similar amount of the classes. That means a similar amount of labeled samples per class in the training and the testing data set. So we were talking about the likelihood function, and the likelihood function depends on the data. So I told you when we have training data, we can compute the likelihood. So let's have a look first at the data. So remember, we had this small image patch from the desert with this crop fields, and here you can see the feature space with red, green, and blue. And all the samples from the image are collected in this feature space. And remember what I told you about natural images, and that vectorized images in the feature space do not cover the whole feature space. Instead, the space is only sparsely filled. And this is also generally the case for intensities. So it's when you have natural images and you put all the intensities in such a feature space, it's mostly sparse. And when you illustrate this for this example, you can already see that the green, so this green arrow lands in one corner of the feature space, and the desert is in another corner of the feature space. And this can also be seen if you color the feature coordinates in their respective label color. We use blue and red, and because we only can learn the model with the training data, we restrict ourselves in the following step to only use the training data. But as you can already see here, there's a nice distinction where the arable land is and where the desert is. What we compute now is the likelihood function value. So this is what we wanted, and we have one assumption for now, and we assume that our data is Gaussian distributed. And here you can see the equation for a Gaussian probability density function, which is parameterized by the covariance matrix sigma and the mean mu. So we assume that we have such a Gaussian probability density function for each class. That means the index k. And there are different parameters. That means a different covariance matrix and a different mean for each class. That's why we have this index k, because we need one such function for each class. And d in this equation is the dimension of the feature space. So this function can be computed in arbitrary feature dimensions, and n is the index for the training samples. And this is actually an assumption which is done quite often, and it works quite well for a lot of applications. But of course, you can also use other distributions than Gaussian distributions. But for now, we assume our likelihood is a Gaussian, follows a Gaussian distribution. So what we now need to compute is the parameters of a Gaussian distribution. That means the covariance matrix and the mean. So we have given our training samples. Our training samples are denoted by phi n, and you have vectors, and we can collect all the training samples in one huge matrix. If you only take training samples from one class, you have a class-specific feature matrix. And the mean per class is nothing else than taking the average of all feature vectors which belong to one class. And the covariance matrix is computed by the mean reduced feature vectors per class. So you have once you have computed the mean per class, you can reduce this feature matrix, this class-specific feature matrix, by this mean, and then you can compute a class-specific covariance matrix. And the mean vector now has the dimension of the feature dimension times 1, and the covariance matrix has the dimension of the feature dimension times the feature dimension. So on the diagonal of the covariance matrix, you have the variances in each dimension of the feature space. And when we have a look at one dimension, for example, the red feature, then the likelihood can be illustrated like this here. So indicated in red and blue are the number of samples per class per red value. And this is nothing else than a histogram. So on the x-axis you have the red values, then you count how often this red value occurs. And then you have two curves in there for the two classes. And the curves in red and blue are the computed Gaussian density functions, parameterized with the mean and the covariance. So where you have the peak, this is actually the mean of the specific class. So 1D likelihood can be illustrated with the histograms. In 2D, it looks like this. So now you have two feature dimensions, for example, degree and the red feature. And it looks exactly like this, that you have all these scattered feature vectors, feature coordinates. And the red and the blue lines here are the 1 sigma isolines of the Gaussian distribution. That means all data samples in there are less than 1 standard deviation away from the mean value. So when you have these ellipses, the center of the ellipse is actually the mean of the class-specific distribution. And because we have three features, so we have red, green, and blue. This is what our feature, our feature space would look like. And now you have ellipsoids. So these yellow ellipsoids are the 1 sigma ellipsoids, and they can be interpreted in the same way as for the 2D Gaussian likelihood. So the center again will be the 3-dimensional mean of the class-specific distributions. So what we saw now is how we can get this likelihood function. And so all training samples are described by a class-specific likelihood function. And if the likelihood function is a probability density function, the area must be 1. This is nothing you need to do, but you could do it, and then you would you would have a probability density function. But do not forget, from a likelihood function, you cannot derive probabilities. If you would have two such likelihood functions for each class, and you would get a value from exactly the same position, that means for the same feature, then you could normalize it, these two values, and then you would end up with a probability. I will talk about this in more detail later on the slides, because when we talk about Bayes' theorem, you always have a choice if you only want to have a value for a decision or if you want to have a probability. But for now, let's focus on the likelihood function. I showed you we assumed our data is Gaussian distributed, so we use the Gaussian distribution, but there are also other functions which can be used, and they are parametric and non-parametric methods. So let's have a short look on what it means to have a parametric and a non-parametric approach. So we used a parametric approach because we used a Gaussian distribution, and when you use a parametric approach, a parametric form for the likelihood, it leads to a fixed number of parameters. Our Gaussian distribution is defined by the mean and the covariance matrix. That means you always have these kind of parameters, and your whole data is described by these parameters. In the other case is that you use non-parametric approaches. It does not mean that you do not have parameters. It just means that you do not have a fixed number of parameters, and you use the data to you use the data to define the distribution of your data. It can be the whole data set or just a part of it. And a good example is k-nearest neighbor. Here, remember, the whole training data set given was used as representation for it. And this can be done with the whole data set or just a part of the data set. And as you can see, or when you think about it, the more training data samples you have, the more data is used to define the distribution. So non-parametric models grow in size to accommodate the data. And so it's can be much more efficient to use a parametric method, but here you make assumptions, for example, that your data is Gaussian distributed. So let's go back to our likelihood function, and based on this we can already define a classifier, and this classifier is called maximum likelihood classifier. So for this you only need your likelihood functions, and as the name says, for a specific value, for example a specific feature, the red value in this case, you look which one of the likelihood function gives you a larger value. So when you pick a value at the x-axis here, you take these two curves, which are your likelihood function for each of the classes, and then you have a look which function value gives you the larger value, and the maximum is an indicator for the class membership for exactly this feature. And in this case, the decision boundary, because you want to have a classifier, so you need a decision boundary. In this case, the decision boundary is exactly where these two Gaussian curves intersect. And this is reasonable because here's exactly the place where where it would change that this function value is the maximum for a specific class. So on the left side, the function value for the red class would be larger, and on the right side, the function value for the blue class would be larger. And to make it a little bit more formal, so what you need to do to do a maximum likelihood classification is, first of all, the training is that you estimate the likelihood function. That means you first of all assume something. For example, your data is Gaussian distributed, and then you compute the parameters of the Gaussian distribution, the mean and the covariance matrix. For the testing step, you derive then the likelihood function value for all classes for specific test samples. And one example is illustrated here. If you have two classes, you would, for example, get a likelihood function value of 0.3 and 0.2. And then there's an optional step, because you can transform these two function values into probabilities. And for this, you normalize that they sum up to 1. And yeah, this is an optional step, because in the end, if you take the argument of the maximum of the likelihood function, you will get the estimated class membership, either if you take the likelihood function value directly or you take the probability. So this would lead to the following result. As I showed you in the beginning, we took some training data, and we learned a model with it, and then you perform maximum likelihood classification. This would be the classification map, where red is the arable land and blue is the desert. And here's the normalized likelihood function values, which can be interpreted as probability. So bright means a high probability, and dark means here's a low probability. And so let's come back to the Bayes theorem. So far we had a look at the likelihood function for specific classes K, and I showed you how to compute it and how we can already get a classifier from it. But sometimes, you also have prior knowledge about how often a specific class will occur. And so let's have a look at the prior probability. And you will see that once we had a look at this value and integrate it in our classification, we will end up with a maximum a posteriori classifier. And to illustrate this and to go through such an example, let's define a classification task. The classification task is to classify the image into 3 different classes, namely crops, desert, and fruits. And so now you need prior knowledge. And when you think about what your prior knowledge about the occurrence of fruits is in the desert, you will know maybe now, or even after some research in the internet, that it's quite improbable that farmers will deal with fruits in the desert. But let's assume for now you have this class and you need to classify also if a pixel belongs to the class fruits. And so we have three classes. Assume now, so what you want for now is you want to know the posterior probability for each of the three classes given a specific feature. And specific feature means, for example, a pixel or a segment. So you want to classify one feature which is assigned to one entity in the image. And you already determined the likelihood function, and for the specific feature, you get a likelihood function value for each of the three classes. And here it's 0.3, 0.2, and 0.7. And then you have some prior knowledge. And this prior knowledge is how likely a specific class will occur. And here you use your knowledge you have, and you say, okay, for crops, for the arable land is 0.5, for desert is 0.4, and for fruits it's 0.1, because you know it's not so probable that fruits will occur in the desert. And now you need to compute the evidence. And to compute the evidence, you pointwise multiply the likelihood and the prior. So you take this 0.3 times 0.5 plus 0.2 and 0.4 plus the 0.7 and 0.1. So this is the pointwise multiplication. You sum over all classes, and in the end you end up with 0.3. And this is your normalization that you ensure in the end that you have posterior probabilities. And to compute now the posterior, because this is exactly what you want to have, is you again pointwise multiply the likelihood and the prior, and then you divide by the 0.3. And so now you do not sum, because you want to have the posterior probability for each class, otherwise you would end up with 1. And if you write it down and you compute it, you will end up with 0.5 for crops, 0.3 for the desert, and 0.2 for the fruits. That's all. And I think once you test it and you go through such an example, it's not so much magic anymore to do a classification with the Bayes theorem. So in order to perform a maximum a posteriori classifier, this is what is actually was shown on the last slide, is so first you train, for the training you estimate the likelihood and you choose prior values. Either somebody tells you this or you have this knowledge. Then you, for the testing, you derive the likelihood function values for our classes, because the likelihood function is determined in the training. Then you multiply with the prior values, and then you normalize. And again, you want to make a decision in the end. And for this, you take the argument of the maximum of the a posteriori probability, and this is the estimated class membership. And as I said, the normalization is an optional step, because the decision would not change, but sometimes it's nice to have such a probability. And when you compare the maximum likelihood classifier and the maximum a posteriori classifier, you will realize that both classifiers will give you an identical result if the prior values are equal for all classes. So this is also what you do when you do not have any idea about if you do not have any prior knowledge about your classes, just assume it's the same probability. So this has the same effect just at leaving it, not considering it. But in case you have prior knowledge, use it. And here's again the comparison where the decision boundary is. On the left side, this is the likelihood function. On the right side, this is actually the posterior distribution. And yeah, if you have the same prior, you would end up with the same decision boundary. So that was how you can perform classification with Bayes' theorem. And the question is now how to evaluate the classifier, because it's all nice when you have a classification result, but of course you want to know how good your model is. So for evaluation, you have two possibilities. I already mentioned this in very briefly in the last lecture. One possibility is to have a qualitative evaluation. That means you have a visual interpretation of the classified images. Here, there's not necessarily labeled data involved. You use the labeled data to have a quantitative evaluation. So here you compute accuracy measures, and also this is more objective because this is supported by numbers and by graphs. And so you should always try to have both evaluations, but in any case, you should always try to get a quantitative evaluation. So let's assume for now we have only two classes. What you always have is you have an estimated label and you have a reference label. So now you take the testing data I told you to put away for the training. Now you take it and you make the evaluation with it. When you only have two classes, you can also talk about a positive and a negative class. This can, for example, apply to foreground, background, or object, non-object, something like this. It's typical classification task you can find in many applications. So when we talk about only two classes, you mostly talk about, when you do the evaluation about the true positives, false negatives, true negatives, and false positives. And when you have a closer look at the name, at the term, you will realize what it means. So for example, the true positives are positive examples classified as positives. For example, false negatives are positive samples classified as negatives. So the true, if there's a true in the word, it's good. If there's a false in there, it's not good, because then your classifier made a wrong estimate. It's a wrong decision. And you can put it in such a confusion matrix. And this confusion matrix has a dimension of 2 times 2. And you need to decide on one dimension is the reference and the other dimension is estimation. Please be aware, this is not consistent in the literature. It can happen that the reference can also be in the rows, and the estimated labels can be in the columns. And here, what you do is you just count how often specific combinations occur. So, for example, when is the reference positive, and when is the estimation actually positive, or when is the estimation negative? And you count this for all combinations, and then you put it in this matrix. And you can do this also for more than 2 classes. But now we do not speak about positive and negative. We just talk about the classes. And here again, I want to point out, you only do this for the testing data, except you're interested in the training accuracy. But for evaluation, you need to have a look at the testing data. And coming back to our example of crops, desert, and fruits, you have three classes. So you have 9 values in this confusion matrix. And the diagonal is exactly all these samples which were correctly classified. And imagine for now, you counted how often all these specific combinations occur, and you put them on this in this matrix. And you can do some further analysis, because in the end, confusion matrix is quite nice, but you want to have easy understandable numbers for your accuracy measures. So when you sum, you can, for example, test that you got all combinations, and you make the evaluation for all given testing data. So the 240 are exactly the number of testing data samples you have. You can do this for all the classes. So you have 120 reference samples for crops, 100 for desert, and 20 for fruits. So 240. If it doesn't add up to the number of testing samples, you made something wrong in filling this matrix. It's always good to make this check. Then if you go to the rows, and then you if you take the sum there, this is the actual number of estimated class labels. So for example, 20 samples, 20 samples were classified as fruits, 105 as desert, and 115 for crops. And now, as I said, you want some numbers, some more summarizing numbers. And we first have a look at the overall accuracy. The overall accuracy is when you take the diagonal of the confusion matrix, and you divide it by the actual number of referenced testing samples you have. In this case, we have 190 are correctly classified, 240 we have. So it's roughly 79% overall accuracy. So in remote sensing, we quite often talk about user accuracy and producer's accuracy. And these two values, or these two terms, refer to nothing else than actually the sums, which I showed you on the last slide. That means when you sum over the rows or when you sum over the columns. But let's have a closer look what it actually means. So when we talk about user's accuracy, it means from a user's point of view, how accurate actually the derived classification result is. So you start from the result, what you produced, and then you have a look how many pixels are actually the class as they were classified. And the producer's accuracy, here it's from a producer's point of view. So you start here from a reference, and you have a look how many pixels are correctly classified. So here you can see exactly this illustrated. So let's assume you have two maps. So on the left side, there's the reference map with the two classes. This is actually what you want to have. On the left side is a classification result. And this is what you got, what you estimated. And you have 1000 pixels overall. And now for the user's accuracy, as I said, you come from the results, so from the map on the right side. And you want to know how correct it is. So you have one red pixel, and actually if you look then, if you go to the reference, you see, this one pixel is correct. And then starting again from the results, you have 999 pixels for the blue class. And when you have a look at the reference, you see, 900 of them were classified correct. So you have a user accuracy for the red class of 100%, and for blue it's 900 divided by 999. This is roughly 90%. For the producer's accuracy, it's the other way around. Here you start from the reference, and then you have a look at the result. So in the reference you have 100 red pixels, and you have a look, and only one pixel in the result is actually correctly classified. So you have only a classification accuracy of 1% for the red class. But if you look at the blue class, you can see all of the blue pixels in the reference were classified correctly. So the accuracy is 100%. And as I said, this can be seen exactly in when you sum over the rows and the columns. So this can be seen in the confusion matrix, but on the last slide it was a little bit more illustrative. And there's another accuracy measure which is quite important, and I recommend always to use also or to compute the average class accuracy, because imagine the following example. You have you want to classify in a satellite image forest and lake, and it's a scene from let's say Amazonas forest, and you have a huge forest, and at some point there's a few pixels which belong to a class lake. And so if you classify the whole image as forest, you will get a very high overall accuracy, which is nearly 100%. But actually, this does not really reflect what was done or what the classifier did, because it should also reflect how good it is in classifying all the classes. That means forest and lake. So, and for this, to reflect this, you can use the average class accuracy. What is done here is you compute the accuracy for each class, which is 100 of 120 crop pixels were classified correctly, 80 out of 100 were classified correctly for desert, and 10 out of 20 were classified correctly for fruits. And then you compute the accuracy for each class and then divide by the number of classes, and here you get a percentage of or accuracy of 71%. So every time you have an imbalanced data set, and with imbalance I mean a different size of classes, you should also do this. If in case all the number of testing samples in each class is the same, you will get the same result as for the overall accuracy. Another quality measure, another evaluation measure, which is used quite often in remote sensing, is the so-called kappa coefficient. It was invented by Cohen, that's why it's always sometimes also called Cohen's kappa. And kappa measures the difference between the actual agreement and the agreement by guessing. So in case you would just guess what it is. And it takes values between -1 and 1. So I always think a little bit as it has a different characteristic as a correlation coefficient, which is also between -1 and 1. Totally different equation, but from thinking about it, it helps me to understand it. So the equation is here. The equation includes the overall accuracy, and there's then a more complex term. I denoted it with A with an index E, and E is includes the producer's accuracy, the user accuracy, and also all entries in the confusion matrix. So here the whole characteristic of the confusion matrix is captured in this value in order to get such a that you can produce such a characteristic of your classification result. So this is always a good combination, that you produce the overall accuracy, the average accuracy, and kappa coefficient. There are some more. It always depends on your application process. So think about it, what would be good to show others how good your model is and how good your classification result is. And one last thing I want to add is the so-called cross-validation. Because when you have one classification result, it might be good, but it tells you nothing about how stable your classification is. It might happen that you were lucky with your training and testing split. So that's why cross-validation is good to use it for evaluation. Let me show you the principle of a threefold cross-validation. So what you normally have is you have training and testing set. Generally you use more data for training than for testing. So let's assume for now you have 3 folds, and 2 of these, that means 3 sets. 2 of these sets are used for training and 1 set is used for testing. What you can do now is, for this you get 1 classification result and you can do the evaluation, but you can also change the sets so that each set serves once as a testing set. And so in the end you have 3 different models, 3 different classification results, and also 3 different evaluation scores. And what you do in the end is you can take the average, but also report a standard deviation. And the standard deviation is it gives an indicator on how stable your classifier is. Mostly you do it for at least 5 to 10 runs. That means 5 or 10-fold cross-validations. The more you have, of course, the more tells it about, the more it reflects how stable the classifier is and what the actual mean accuracy is. But yeah, this is for illustrating the principle. But here you need to be aware that the same rules for splitting apply as for splitting the training and test data once. Because you need to see that in each of the set all classes occur, and also that it's not such a huge class imbalance. And as I said, besides the average accuracy, that means the average overall accuracy or the average class-wise accuracies, it's also good to report the standard deviation when you report your evaluation results. With this, I want to conclude. What learned you today? You learned about probabilistic classifiers. I told you how you can use Bayes' theorem to make classifications. We were talking about Gaussian maximum likelihood and Gaussian maximum a posteriori. And of course, this is not restricted to Gaussian distributions. You can also use other distributions or non-parametric approaches to get some density, some distribution of your data. This is what I'm talking about next week. And we were also talking about evaluation of the results. So I told you what the confusion metric is and what you can see in such a confusion matrix. And we were talking about cross-validation. But please, every time you solve an application, think about what would be useful for others and also for you to get an impression how good your classifier is, how well it performs on unseen data. And with this, thank you very much for your attention, and I hope we will see each other next week again.